Okay, let's continue. Okay, so if there was no acceleration, it would just be a straight line, right? And the velocity is just given by the slope. And you know, like over here, it would just be, the slope would be point, at each point would be pointing in the same direction. So if there's no acceleration, the position would just look like this. It would linearly increase at a steady rate, right? But because we have acceleration, we have this curve to it. So let's look at so if this is the position vector, I'm sorry, position function, what would the velocity look like then? What kind of curve or what kind of function do you expect the velocity to look like?
A straight line?
Linear.
Yes, a straight line, right? Because we know that acceleration is linear. Exactly. Right. This is the acceleration. Let me just write it over here. And our starting point is at 0. There's no y-intercept, or the y-intercept is 0. And then the slope is just 2a. Right. And that's our acceleration. And then I'll erase this. And then what do you expect the acceleration to look like? So if we plot it, what?
A horizontal line.
Exactly. The acceleration is a constant acceleration. So over time, it doesn't change. And it's given by over here, which would be that 2a. And it's given by 4.2 here. Right? A is just a constant acceleration. Everybody, it's clear? Okay. Okay. Now let's actually derive the a set of equations for motion with a constant acceleration. For the most part, mostly we could we deal with the constant acceleration, or we could approximate it as a constant acceleration, right? Apply a constant force, and then it will be a constant acceleration. So let's derive the equation, the equation to motion for constant acceleration in one dimension. Remember, we're only working in one dimension here. And then once we figure out one dimension, we could scale up to 2 and then 3 dimensions. So this is section why don't we erase that? It's taking up valuable space on the board. So this is section 2.5 from the book. All right. So, and these, so we'll start off with whenever we derive or solve a problem, it's good to write down the set of equations that you'll use to derive some final result in this case. So, well, let's write down our formula for, we have basically 2 formulas right now. The average velocity, which is given by delta x over, we'll just call that t, delta t. And then this is equal to x. We'll call the final position x here. And then the initial position, which we'll generally use for the entire course, the initial position will be given by this x naught. And let me switch to black for this. And over t minus t naught. Right? And now we can take the starting time to be arbitrary. We could set it to anything we want. And obviously the simplest thing is just to get rid of this t naught here, right? And so then it'll become this t. And t is just the elapsed time when you start recording, you know, however long you record the time for your thought experiment. All right. And then the acceleration is going to be assumed constant in time. And what this implies is that the acceleration is given by the change in velocity over time, right? Now, since it's constant, this is no longer average, right? Because it doesn't change, like we showed previously, right? So now, let's plug in. Let's solve for v here, right? Let's put v in terms of a, right? Because, all right, so let me rewrite this a little bit differently. Now v changes over time, right? Because there's an acceleration. So we'll have something that looks like this, actually, right? So we have this function that changes over time. And the acceleration is just a constant. So we actually want to solve for v. It's more meaningful, right? Because the v can change. So we'll solve for v, and we'll bring everything over to the other side. So v, and then when we bring t over, we'll get this, right? So whatever initial velocity you start with, plus the acceleration over the amount of time. And if you think about it, it makes sense. Spend a little time pondering it, make sure it makes sense to yourself. But it does. So at each increment of time, the velocity increases by that acceleration amount. Right? Now we have an equation for v. Let's go to x, right? So now we'll use this formula for x. So we have this. Now this is the average velocity that we have. We have xt minus, I'm rewriting it up there to express that x can change over t. And it's the same formula, and we get the same result, just different, just with the position vector now. XO plus the average t, right? Now, we don't want the average. Sometimes we do. If it's useful, we'll use this one to simplify our lives, but these are important formulas, so I'll circle them. But this doesn't fully describe it if we want the instantaneous velocity at, for using the instantaneous velocity, which describes things much better than using the average velocity. So let's figure out how we can replace the average velocity by the instantaneous velocity, right? Now, so let's see if somebody can get this. Don't look at the book. If you did, don't worry. Don't shout out the answer. I'll give you a second to think about it, right? So when we have a constant acceleration here, right? We're making this assumption that we have a constant acceleration. So the velocity looks like this, right? So the average velocity, right, is just these 2 points, V1 and then V2, and we take the average, right? So this would be the average, right? This is V0, right? How can we describe this in terms of the instantaneous velocity? Or let me rewrite this as V0 and then V sometime later, right? We're looking at it at some time later. So what's the formula for average, for an average? Right? We just, sum up all the quantities and then we take the number of points that we take, right? In this case, we'll have the average, we have 2 points, and then we have the average over here. So we divide it by 2. I'm sorry, plus. And we have this, right? This is the average velocity in between. Does everybody see that? The average velocity is the midway point between these 2 quantities. That's what we're doing over here. And this only works if we have a constant acceleration, right? Only here will the average be the midpoint between V0 and then some V later. Right? This won't work if we don't assume a constant velocity. So we'll use this formula. So that means that now we can replace V0 by this, V average by this. So let's do that. Right? Now we have 2 functions of t. We have x and then we have vt, right? This is not a fun function to use when you're doing calculations because you need to know vt to calculate x. We could simplify this, right? We have a function for vt already. That's solely dependent on t, right? T is expressed within this function. Over here, t is some other function within v. Over here, it's expressed explicitly. So let's plug in for vt over here, and we get this. right? This is t. So usually you put a little scribbly at the bottom to get rid of this little curved structure at the bottom to differentiate with plus. And then finally, when we simplify it, we'll get this x plus, you get x plus v naught t plus 1/2 a t squared. Okay, we'll get this in the end. I'm going to erase this and then just put this as the answer so that we can see it together, everything together. And this is the third formula in our toolbox, right? And then now we can calculate the position. If you give me the initial position, the initial velocity, the acceleration, I can calculate its position, the rocket's position at any time. Very, very powerful, right? Now, if we're in the 16th century and we have a trebuchet, you know, the thing that launches the projectiles, we could calculate now using this how much initial velocity we need to apply to send it a certain distance, right? Well, you need a little bit more than this, but now we have a much more higher advantage over our neighbors in the next castle, right? Is a very big step forward, and it's pretty simple, right? The way we derived it, you know, we just took this idea of average velocity and acceleration. We didn't even need calculus for this, and then we were able to get these positions, its position over time. Given, of course, the major assumption here is a constant acceleration. Now we can rewrite this. Like, let's say if we don't have t, we could rewrite this in a form that doesn't involve t. So if we take this, and instead of using a over here, we solve for t. If we solve for t, we'll get v minus v naught over a. So now instead of plugging in the t over here, or instead of using t, we use a, and you could look it up in the book for the exact derivation, but it ends up coming out to be, so I'll write it at the bottom. So we have this. We'll start over here again, and we'll have Vt plus V naught over 2 times t, right? And then we'll plug in that, and we'll end up with this plus all right, the same formula. Now we plug in t for that, and we end up with this And then when you expand this, because you'll have V naught over here, this will cancel out with this V squared over here if you look. And in the end, you'll get this function. Right? In the end, you'll get this function. Right? So these are the important kinematic equations. And we should also include what I had just up right over here. This is also a very critical formula over here, right? And in the book, they don't include this equation over here because it's kind of redundant with this one, right? In a very general sense, this is redundant almost. Well, really, this is the most precise one. But this can be useful as well if you're given an average velocity. So these equations will be used to all the time for the next few weeks or next few lectures. So, and then you can fully describe a particle's motion under the counts of acceleration using all of these, right? And we use the bottom one if we don't care about time or we're not given time. So for problems, what you'll do is you have to look at the initial parameters that they give you. Oh, after a certain amount of time, this happens. Oh, so then I know that time is important over here. Or if you hear a problem like the ball travels a certain distance when, which is this x minus x naught, and has under a constant acceleration, and it starts at rest. Right? At rest means the initial velocity is 0. And then you're given the acceleration and you're given the distance. And if they ask you for a final velocity, use this to calculate it. So it's very important to write down all the parameters that you give you that are given in the problem. So so let's do some problems now. All right. Let's do a few problems. Right. So let's say we'll do example 210. So now this is section 6. Right. Now the first thing to do when you do a problem is obviously read it. How long does it take a car to cross 30-meter wide intersection after the green light turns, after the light turns green, if the car accelerates from rest at a constant acceleration of 2 meters per second squared, right? So I read it. Next thing to do is you reread it, and while you're rereading it, you copy down the information and draw a picture. It's very important to draw a picture. Even if there's a picture given to you, it's valuable to draw it yourself. It helps you intuitively understand the problem. So the car is at an intersection, right? So we have a car, At an intersection, we'll draw the light for fun. Right? And then this is the intersection. I'll draw it. I'll describe it by a blue line, let's say. You can't see the blue line. Right, a green line, which you'll see, it's right over here. And this intersection is 30 meters. Right, and I see what's given to me. And if something's given to me on the page, I can write it down in the problem. So once the car starts moving, it goes with a constant acceleration of 2 meters per second. Right? And it keeps that up for later, right? I'll just draw it like this. Right? Now, let's figure out where our origin points are, right? So when's our zeros, right? So when's our time of zero that we'll call that the starting point of our analysis? It'll be when the light turns green, right? That's our starting point. So t equals 0 is when the car starts moving, right? Okay. What's our initial velocity? Anybody? Well, we look at the problem. It starts from rest. What does that mean? It's 0. Starts from not moving, right? And then where do we take our 0 point? Our x naught. Conveniently, we'll take it actually over here. So we'll follow our point of motion is the front of the car, right? It's just easier to visualize it because that's when it's crossing the intersection, right? So we're given this, right? Anything else that we're given? We're given the distance, right, that we travel. Anything else? And then V naught is 0. So this is over here. And then at this distance over here, let's erase that. At this distance, we have x is equal to 30 meters. We don't know v. The acceleration, well, the acceleration is constant. And the time is unknown, right? So we're just analyzing the problem. Sorry, guys, I didn't see the chat. Okay. Right. And the problem asks for is how long does it take to cross the intersection? So what we want to find is this t, right? This is what we want to find. So we're given these initial parameters. Let's see what we could use, right? What do we want to use for this function? If we want to find t, how long does it take to cross this distance? So the first thing that comes to mind is this one, right? The position function, obviously. So this is given by x naught plus v naught plus a over t squared. Next, we look at is what's in this problem. What do we know that's in this problem? Do we know x naught? Yes. Do we know v naught? Yes. Do we know a? Yes. Do we know x at the time later? Yes. There's only one parameter that we don't know, and that's t, right? So we can solve this problem without using any other equations. Now, let's say if I'm not given something. Let's say I'm not given the initial velocity, right? What we need to do is we need another equation to solve this. So there's a general rule. To solve a problem, you need as many equations as you have unknowns. So usually you like to start off with the equation the general equation that will solve the problem in one shot. And you see what you have in that equation and what you don't have, right? And then you use other equations available to calculate what you don't have. And the general rule is how many equations you have that are available to you has to equal the number of unknowns in the problem. And then you can solve it. Here we have one unknown and we have one equation, so we can solve it. So let's solve it. So when we plug everything in, we have 0 plus 1 over 2 times 2a, right? We'll leave a alone. And then here we'll find, and then x, of course, is 30. Oh, we'll leave that the way it is. So then, in general, x is this simple function, right? Now let's plug things in to solve for t. We want to calculate it when it's at 30. And then we have 2, the acceleration is 2 over here. So then now we solve for t, and it's just the square root of 30.
Seconds.
Yes, 30. Well, it will be in seconds, yes. This is actually in meters right now. All right, so yeah, let me explain that. Thank you for actually pointing this out. So we have 30 meters, right? And then we have 2 meters per second squared of acceleration times second. So let's follow the dimensional analysis, and then we'll have 2 times 2. And then over here is meters per second squared. Oh no, we're bringing it over to the other side. So I was right. Meters per second squared. And this is over the square root, right? So what happens is that the meters cancel out. Since it's the reciprocal of a reciprocal, this comes up top. And then it's inside this square root. So we get rid of second squared, and we're left with this quantity. All right. And it works out, the units work out, right? Now, the solution to this is actually, there's two solutions, right? Square root has two solutions. The plus and minus of this, right? Because when you square it, it doesn't matter if it's positive or negative. So it's ambiguous in this sense. Now, what we say is, let's look at these. So what do we do now, right? We have two solutions mathematically, right? This is where the mathematics and physical reality sort of diverge. What does negative time mean? It means the time before it started moving, right? And this represents the time, if it was under the same acceleration, the time before it was moving. But that's not what we care about in the problem. We just care about it crossing the street. So we just use a little bit of reason and say that the negative symbol is unphysical. It doesn't make sense. Obviously, it doesn't make sense because we're only studying from time 0 until it crosses the intersection. So we just get rid of this. We'll just leave it as a positive 5.48 seconds, right? Now, did we do this problem right? So based on what it's given to us, right? How long does the car take to cross the 30-meter wide intersection, right? So did we make an error in our assumption? Or did the book make an error in its assumption? Can anybody think about the error? So let's think about it. This car is traveling, right? Now when it gets over here at t is equal to 5.48 seconds, what does this look like? Right? It looks like this because we're taking this point to be, we're following this point on the car. Has it crossed the intersection at this point? No, it hasn't, right? You don't consider a car still in the intersection, as having crossed it. So they didn't take this into account. They didn't tell us the car length, and so they made a little boo-boo in the book. Somebody wants to contact them, please do. I wonder if they fixed it in later editions. So, okay. Let's take, how much time do we have left on this? Okay, it's gonna end in 1 minute. Let's start at 1:10. I want to try to finish this chapter. So I'll see you guys back at 1:10.